So now we're going to talk a little bit more about the stress cube, and we're going to talk about the equilibrium, because we started off with a potato, like this, all right, and we said that we took 3 different slices that were oriented with our 3 coordinate system axes. So we had one cut that had a normal vector in x, one that had a normal vector in y, and one that had a normal vector in z. And when we did that, we were left with 1/8 of the potato, and we could figure out the components of our traction vector, of our stress, on each of those faces. And I ended it with saying that was actually only 3 of the faces. And what we really wanted to get down to was a cube. And in order to get down to a cube, we'd have to make 3 more cuts. So we end up having 6 cuts, and we end up having 3 components per cut. So I'm going to show you now, this is our stress cube in physical form here as a little prop. And so you can see now I've changed some of the colors so that we can kind of start to talk a little bit more about equilibrium of this guy. So you can see that we have one red pointer that's going in the x direction, one green pointer over here that's going in the y direction, and one blue pointer that's going in the z direction. And you can see that for each face of our stress cube, we have 3 different components. One that's in the x direction, that's denoted in red in all 3 cases. One that's pointed in y, which is going to be green in all 3 cases. And then finally in z direction, the blue ones. Those are all pointing in the same direction as well. And so we're going to end up looking at these different stress components, and we're going to look at equilibrium to figure out exactly how many of these components are independent. As it turns out, we start off with 6 faces times 3 components each. That's 18 components, but we can actually reduce that down quite considerably. So let's start off with our cube here. It's going to look something like this, and I'm going to draw some dashed lines here because we're going to end up having to talk about the back of the cube as well. And just to give you some little asides here. So this is our cube, and our cube is shaped, we have a delta x here. I should put our coordinate system, excuse me. So our coordinate system looks something like this. There's x, there's y, there's z. It's going to be some distance delta x in the x direction. It's going to be some distance delta z in the z direction, and some distance delta y in the y direction. So the total volume of this guy is just going to be delta x times delta y times delta z. And we're going to have a sign convention when we talk about some of these different things. So we're going to make sure that our positive direction, our positive arrows point in the positive direction. So on one face, so the face that we've been talking about, those orient themselves in the same direction as the positive axes. So if this is positive x, we have a positive vector here and a positive vector there. If we're talking about in the y, this is a positive arrow in the y direction, a positive arrow in the y direction as well. On the back side, we actually end up having to flip things around. So now a positive vector on the back side points out, and a positive transverse vector points down. So we're going to do the same thing over on this back side. So we're going to end up having to remember this when we go and do our equilibrium. And so now I'm going to draw some of these arrows. So we're going to start off with looking at the equilibrium in the x direction. And so on this face, we're going to have our sigma xx. That's our normal component. On our top face here, we're going to have our tau yx. So it's on the y face in the x direction. And we're also going to have another vector down here, which is going to be our tau zx. So I'll put that right here, tau zx. So now in addition to those, so those are all the ones on the front side, but now we're also going to have to think about all the arrows on the back side. And so I'm going to draw that in a slightly lighter green, so hopefully you can see those. All right, and that's going to end up going that direction. So that guy there is going to be tau z x. So it's tau z prime x. So that's going to be on the z prime axis, the back side. We're going to have the same thing down here. So that's going to be the tau y prime x. And I'm going to end up having a normal component out here, and that one's going to be sigma x prime x. All right, so now you can see that we end up having 6 components all together that are all going in that x direction. So x equilibrium, we'll do down here, and remember these are all stresses, right? So we're going to need to multiply those stresses times areas in order to get a force. And I'm going to think first about all the things that are multiplied by delta y, delta z. Okay, so that would be delta y, delta z. That'd be these faces. So on one side, in the positive x direction, we have a sigma xx. And on the other side, we end up having a negative sigma x prime x. Now let's do the same thing with our other components. So now let's do a delta x, delta z. All right, so that's going to be delta x here and delta z there. So that's going to be the top and bottom of our cube. So now we have a positive tau yx, and we have a negative tau y prime x. And we can do the same thing for our last area. That's delta x, delta y. And that's going to end up being delta x and delta y. So that's going to be our front face and back face here on this side. So that's going to be a tau zx minus a tau z prime x. And all that, in order for this to be an equilibrium, has to equal 0. So just to kind of reiterate here, this stuff here, this is our area, our little infinitesimal patch, and this is our stress. So these are both stresses, and they're the stress components. And so now we can think about some of these different, we want to ask ourselves, what does this tell us? And at the end of the day, we're going to do the same kind of trick we've done with all of our other equations, and that's we're going to look at what happens as this infinitesimal cube gets smaller and smaller and eventually approaches 0. So the limit as delta x approaches 0, what happens? Well, you can see that this term here is going to go to 0. This term here is going to go to 0. And what we're left with is just going to be this front part. So we get delta y, delta z, and we get a sigma xx minus sigma x prime x equals 0. And the only way for that to be true is if this stuff in here is equal to 0. And that implies that these two things must be the same. And we can do the same thing for our other ones. So let's do the limit as delta y approaches 0. And that's going to tell us, okay, delta y goes to 0, this term goes away. Delta y goes to 0, this term goes away. That's going to tell us that delta x, delta z, times tau yx minus tau y prime x is equal to 0. Sorry, I'm going to try and squeeze it in there. And what's that going to tell us? It means that everything in that parentheses has to be 0 as well. And just for completeness, we'll do the same thing here for z. And as delta z goes to 0, we're going to say, okay, this term goes away, that term goes away. We're going to get delta x, delta y times tau zx minus tau z prime x equals 0. And we get the last expression here, which means that everything in those parentheses are 0. And that tells us that, of course, the stresses on one side of the cube, delta xx, is equal to delta x prime x, and all of the others. So every stress that's on the front side is equal to the stress that's on the back side. They're just going to be in opposite directions. And so this is important. True for other directions as well. So we can do this same process in the y direction and in the z direction. What you'll find out is that while we started with 18 independent components, we're now down to 9 independent components because everything on the back side is equal to everything on the front side. And so there's one last thing that we need to do, and that is going to be to look at the moment equilibrium. So I'm going to draw our cube again here. So here's our stress cube. I'm going to draw our axes again here. So that's x, that's y, that's z. Still see that? Good. And what I'm going to do is I'm actually going to go right about the center of our cube. So I should put some... I'm going to go about the center of our cube, and I'm going to be taking the sum of the moments about the z direction. So we're going to do sum of the moments about z is equal to 0. All right, and so now I'm going to draw my arrows. So on the front, I have tau xy, and I have tau yx. I'm going to also have our equal forces on the bottom, or stresses on the bottom, excuse me. That's tau yx. And we're going to have this one coming down, and that one is tau xy. So those are equal and opposite. You can see the light green ones, those are on the back side of the cube. And you can see that if we take the moment about the center of the cube in the z direction, none of the other components contribute to that moment. So if I can bring back our stress cube here for a moment, let me see if I can put that up here so you can see it. Okay, so we're taking the moment about the center of the cube, about this blue arrow, and you can see that if I take the moment about the blue arrow here, the red arrow and the green arrow are going through the point where I'm taking the moment about, so they don't contribute. And you can also see that the other arrows, in this case the ones that are pointing parallel, are not going to contribute as well, and everything that is going to be about this face as well. So the only arrows that are left that are contributing are going to be these guys here. And that's what we're drawing in our picture. I just wanted to make sure we could see that in our cube as well. So what we end up with for our sum of the moments here, we end up with 0 is equal to, let's assume that we're going to have our right hand rule. So we can use our right hand, our thumb, and that's going to be a positive rotation. So we end up having a negative tau yx. So that's going to be the top, right? That's opposite our right hand rule. And what is the area of that top? Well, that's going to be delta z, delta x. Okay, so that right there is going to be the magnitude of the force. Now we need the lever arm. All right, so if we go from there, the lever arm to that force is going to be delta y over 2. Right, that's half of our cube. And we can do the same thing. We're going to end up with a tau xy times a delta y delta z. So that's the area now of this front face. That's going to be the force. And now we're going to end up with the lever arm. And that's going to end up being delta x over 2. And we're going to end up with 2 more of those, right? One from this side and one from that side. So I can end up taking all of that there, multiplying it by 2. And if I do that, we can do some algebra here. We're going to end up with tau xy minus tau yx, all times delta x, delta y, and delta z. And if we do any of our limits, like we did before, what you'll find is that everything right here in this parenthesis must be equal to 0. So I'm going to write down, this is, so the same is true for the other directions. You can do some of the moments about x and about y. You'll get the same general equation. And so then the note here that I'm going to try and squeeze into this corner is that we started with 18 values for stress. That includes the back side as well. Once we take these into account, that everything on the front side is equal to everything on the back side, and our shear vectors are the same when you flip around the directions. So the shear stress on the x face in the y direction is equal to the shear stress on the y face in the x direction. So these two guys are going to end up being equal. So now we had 9. Once we figure that out, we're down to 6. So we're down to 6 independent quantities. So that's pretty cool. I'm going to put an exclamation point there. Those 6 quantities are sigma xx, sigma yy, sigma zz, tau xy, tau yz, and tau zx. Pretty cool.